our last topic of the year is similar solids. Similar solids have the same shape, but they are different sizes. Two solids are considered similar if the ratio of their corresponding linear measurements are equal. And what's a linear measurement? Well, linear measurements are like the length, the height, the width, the radius, diameter, pretty much all the line parts of any shape we've done. I might have forgotten one, so I'm just going to put etc. in case I did forget one. So, for example, in number 1, we got to build ratios. Ratios typically are in fraction form. So, I always start with the first shape on top, second shape on bottom. Doesn't matter on their size. I just go left to right, what's first. So, on the first one, there's a 12 height. And on the second one, there's a 3 height. So, the heights go together. For the second fraction, the first one is 8 wide. The second one is 2 wide. They go in a fraction together. Last but not least, 20 long, 5 long. Then we have to reduce. What number goes into both 12 and 3 other than the number 1? Well, it's 3. 12 divided by 3 is 4. 3 divided by 3 is 1. What about 8 and 2? Well, it's 2. 8 divided by 2 is 4. 2 divided by 2 is 1. And last but not least, 5 goes in both 20 and 5, and I get 4 and 1 again. So I asked myself, are these shapes similar? Well, yes. We got the same ratio, which is our scale factor of 4 over 1. Let's try to get a number 2. Again, start with the first one, so it's got an 8 height. Second one has a 12 height. Let's see here. We're 6 long and 10 long. And then we have 6 wide and 10 wide. Go ahead and start reducing your fractions. What number goes into both 8 and 12 evenly? That would be 4. 4 goes into 8 2 times. And 4 goes into 12 3 times. What number goes into both 6 and 10? That would be the number 2. 2 goes into 6 3 times and into 10 5 times. And 6 over 10 is the same fraction, so I'm just going to reduce it based on the last one. Since not all of the fractions are equal to each other, only 2 of them are, these ones are not similar. If they are not similar, we don't have a scale factor because there are two or three different fractions. Okay, and last but not least, number 3. We can approach this a few different ways. First, I'm going to start with how tall are these? Well, the first one's 30 tall. If the second we're standing on the circle, it's 25 tall. So, put those in a fraction together. This next one is a little tricky. So, the diameter of the first one is 24, which means the diameter of the other one, because the radius is 10, would be 20. Or you can approach it as radius. Since you know the radius is 10, the radius of this one would be 12. It doesn't matter if you do radius with radius or diameter with diameter. You just can't compare a diameter with a radius because they're not the same, right? So again, you don't technically need all 3, but I want to show you can do it with either one. What number goes into both 30 and 25 evenly? Well, that would be 5 to give us 6/5. 24 and 20. Well, that would be the number 4 for again 6/5. What about 12 and 10? Well, that would just be the number 2 for 6/5. So yes, these are similar. And what is the scale factor? Well, it'd be 6/5. And that's all you have to do. Build your fractions, reduce your fractions. However, what if we're going to start comparing surface area and volume? Because that's what we've been computing, right? So let's hypothetically say I have a scale factor A to B. Well, if I have a scale factor for the shapes, I have the scale factor for the surface area. And it's the same scale factor. The only difference is you are going to square both numbers. Similar situation for volume. Again, you're going to have the AB, but now you're going to cube both numbers. And if you remember when we did surface area, our units, our answer every time was centimeters squared, inches squared, kilometers squared. And volume, it's been feet cubed, inches cubed, meters cubed. So I'm literally just taking those numbers from the units we've been using. And let's try applying this. So in number 4, we have 3 dimensions, right? We have 6/3 for the heights, 14 and 7 for how wide each one is, and 10 and 5 for the length. The first prism is on top, second prism is on bottom on each fraction, and I'm going to go straight into reducing. I know 3 can go into both of the first ones to give me 3/1. I know 7 can go into both of the second fraction numbers. First, not 7/1, oh my goodness. For 2/1, and I'm going to go back to that first fraction. I was speaking way too fast. 6 divided by 3 is not 3. 6 divided by 3 is 2. I made a mistake there. And last one, we're going to divide both by 5 to get, again, 2/1. So the scale factor for these shapes is 2:1. Well, to get my surface area ratio, I take that 2:1, and all I have to do is square it. Two squared is 4, and 1 squared stays 1. Same thing kind of goes for the volume one. I take my ratio from my scale factor, 2:1, and all I have to do is cube it. 2 cubed and 1 cubed. 2 cubed is 8, and 1 cubed stays 1. And so if you're ever asked for the scale factor, for the ratio of the surface area or the volume, as long as you have a scale factor, all you're doing is either squaring or cubing. Okay? Let me know if you guys have any questions on this last set of note for this. Oh my gosh, for the year. It's kind of sad. And let's also make sure this gets in our notebooks.